In this video, we're going to talk about programmer-defined exceptions. So think about the following typical programming scenario. You're deep into some fairly complex section of code, and you come to a place where you could experience an unexpected error, that there could be something that could happen that would violate some important property of your program. So for example, maybe you're going to discover there's a place where you could be out of memory, or there's some data structure that doesn't satisfy some invariant, so a list that's supposed to be sorted that is not, or something like that. And the question is, how do you handle these errors? How do you write code that will handle the error gracefully and not make your program really, really ugly? So a popular solution to this problem in many languages, including Java, is to add a new kind of value to the language called an exception. And we'll have a couple of control constructs for dealing with exceptions. Here is the two that are probably the most popular, and these are as they appear in Java. So we can throw exceptions, and what this does is it causes an exception to be created at this point, wherever the throw occurs. And that exception will simply propagate out of the program. It'll basically halt the execution of the program at that point, and any containing constructs will also throw the exception. So the exception will simply propagate up out of the code that's currently executing until it hits a try catch. So how does this work? Well, we can try something. We can execute some expression here. This will be some expression. And if this expression throws an exception, if a throw occurs somewhere inside this expression, then we will catch that exception, and there can be a binding here to say what we're going to call the exception value. So this is like a let. We'll grab the exception that comes out of here. We'll call it x, and then we can execute this piece of cleanup code to handle the exception in some way. And so the basic idea behind this design for handling exceptions is that the place where you have the exception, the place where you actually detect the exception, might be somewhere deep inside the code and not a very good place for actually dealing with the exception. So what you want to do is get out of that part of the code, get back to some higher level point where you can clean things up, deal with the exception, and then retry perhaps some larger block of code. Here's a little example of using exceptions. So here we have our main method. And what are we going to do? We're going to have a try block that just calls a function x. And if that raises an exception, then we will catch the exception. In this case, we don't do anything with the exception. We just print out a message saying there was an error, and we terminate the program. So we don't do anything very smart, but we do catch the exception and at least print out an error rather than just terminating. So what does x do? Well, x simply throws an exception. So this function x allocates an exception object. This is just a value. This is just a class like everything else, but it has a special property that it can be thrown. So when we throw it, that's when x terminates abnormally, and we end up in the catch block of the try-catch expression back in the main method. Now, in the last couple of slides, I gave you a very informal description of how exceptions work, and it might not have been very clear. And in fact, it's hard, I think, to give a very clear description without some kind of formal description of how exceptions are supposed to behave. But fortunately, we've looked at operational semantics in this class, and so now you're familiar with those kinds of descriptions of language behavior, and I can actually describe to you pretty succinctly how try-catch actually really works. All right, so we're going to give operational rules here for try-catch expressions. And just notice, I just point out here that I have some kind of font problem, and so I had to write in the turnstiles by hand in this slide. So those handwritten characters are all supposed to be the turnstile character. Now, to more important things, there's a distinction with exceptions. Okay, there are two kinds of states that an exception object could be in. It could just be an ordinary value. So when I say new exception object in Java, so when I say something new that's of the exception class, it's just an ordinary value. At that point, it just behaves like any other object. But then there's a distinction when the object is thrown. So when the exception is actually thrown, it becomes a special kind of value, and it gets treated differently. All right, so we're going to distinguish between an ordinary object V, okay, and objects that have been thrown, okay, which are then active exceptions. All right, so let's take a look at some of the operational rules for the exception constructs. So here's one rule for it's a try-catch block. And what this rule says is that if an expression evaluates to an ordinary value, if it doesn't throw an exception, then the result of the try-catch block is just that value. So the way a try-catch block works is you evaluate the expression in the try block. If that terminates normally with a value, then the result of the whole expression is just that value. All right? Now, the other possibility is that you'll evaluate a try-catch block, and when you go to evaluate the expression in the try block, E1, it will throw an exception. So it could result in a thrown exception. So this is this case, okay, is this case, where E1 evaluates to one of these special values that's been marked as a thrown exception. What do we do in that case? Well, we unwrap the exception. We pull out the value that's in the thrown exception. All right, we bind it to some local name, all right, that's named in the catch expression, and then we evaluate the cleanup code. So with the exception value available, we evaluate E2, and whatever the result is of E2, that is the result of the try-catch block. How does throw work? It's very simple. So throw just takes an expression, it evaluates that expression, it gets some value V, and then it marks that value as a thrown exception. So it wraps the value in this T thing, and that indicates that this exception now has been thrown. Now, the only other thing we need to talk about is how the rest of the language, all the other constructs in the language, deal with these thrown exceptions. And that's very simple. We want those thrown exceptions to simply propagate out of any other kind of expression. So for example, we'll just do one example here because the idea is the same for every other language construct. Let's say that we're evaluating E1 plus E2. All right, so the first thing we need to do, of course, is to evaluate E1. And if that happens to throw an exception, so something goes wrong in the evaluation of E1, and E1 evaluates to a thrown exception, well then we stop the evaluation of the plus right there. We don't even evaluate E2. Notice that E2 is not mentioned here above the line as one of the things to be evaluated. So if E1 terminates abnormally with an exception, then the result of the entire addition is that exception. And similarly for all the other constructs, if one of their sub-expressions results in an exception. In fact, if as soon as one of their sub-expressions results in an exception, they stop evaluating and propagate that exception up. The only thing that will stop the exception from propagating all the way out to become the result of the whole program is if it is caught in a try-catch block. There are many ways to implement exceptions, and here is one simple way to do it. So when we encounter a try expression, we will mark the current location in the stack. So we will mark the position in the stack where we encountered the try. So for example, here, say, is our stack. Let's say that the stack is going this way. We encounter a try expression here, so we put some kind of marker in the stack to indicate that there's a try that was encountered there, and then we go on evaluating things inside of the try, which might add more stuff to the stack. Now, when we throw an exception, if down here all of a sudden the throw occurs when we're at this point in the execution, what's going to happen is we're going to unwind the stack. So we're going to knock everything off the stack. We're going to pop all of this stuff off the stack so it's all gone back to the first try. And then we'll execute the corresponding catch. So here we have marked the place in the code where there was a try, and we can use that to find the expression, the piece of the code that has the corresponding catch block, and we'll unwind the stack to that point and then begin evaluation at the catch. So this particular design has the disadvantage that tries actually cost something. So even if you don't throw an exception, you still pay something to execute a try-catch block. You have to at least mark the stack and remember to unmark it, of course, when you pop things off the stack when you leave the try block. So more complex techniques try to reduce the cost of try and throw and also trade off between them. And generally, the thing you want to do is, because exceptions are probably relatively rare in most programs, is to make the cost of try as low as possible, possibly at the expense of making throws slightly more expensive. Now here's a little trivia question about Java. So what happens to an uncaught exception that's thrown during object finalization? So if you don't know what object finalization is, well, when an object is collected, when an object is garbage collected, it is possible to run a method on that object to clean it up before the garbage collector actually deallocates it. And this is called the finalization method. So objects can have finalization methods in Java, and those methods are essentially invoked by the garbage collector. So when the garbage collector discovers that some object is garbage and is going to clean it up, it'll first invoke the finalization method. And why would you want to do this? Well, let's say we have an object, and it might have, say, a file handle. It might have a pointer to an open file or something like that. And now, when this object becomes unreachable, it will be collected by the garbage collector. But if you don't close the file, well, that's going to cause problems. Having lots of open files that are hanging around without the program using them can cause problems later on, especially if you run out of file handles. Usually there's a fixed number of file handles available from the operating system. So the right thing to do is when this is garbage collected is to first close the file and essentially get rid of this pointer, okay, and then deallocate the object. And that is what object finalization is for. So again, you can define a method in Java that will be run by the garbage collector to kind of clean up any resources the object has before it's actually deallocated. And now the question is, if that finalization method raises an exception, who catches it? Because it was invoked by the garbage collector, it's unpredictable when it's going to be invoked, and it's not clear where that exception should be handled. And the answer to the question is no one handles that method, or nothing handles that method. The exception is simply dropped. And so any exceptions that happen during object finalization that are not handled within the finalization method itself are simply thrown away. One of the nice innovations in Java is that exceptions are actually part of the method interface, and they are checked by the compiler. So in the example that I gave at the beginning of this lecture, we had a method x that could raise an exception, my exception, and notice that the declaration of x actually declares that x can throw that exception. So it's part of the interface to x, part of the checked interface to x, that it can raise a particular exception. And why would you want to check this at compile time? Well, the observation that was made actually in the original Java project was that there were many exceptions that could be raised by Java programs, and people easily lost track of what possible exceptions could be raised. They didn't know what exceptions they had to handle. And in fact, when they added this to the language, the compiler would actually enforce now that a method declared every exception it could raise. They discovered lots of places in the compiler where there were exceptions being raised but not properly handled. And so this led to better error handling in the Java compiler itself. And I think people generally agree that this has been a good idea because it helps programmers to write more robust code because they can see exactly which exceptions they have to handle. Now, there are some exceptions to this rule. In particular, there are some kinds of runtime errors that don't have to be part of the method signature simply because it's very hard to check statically that the method would never raise them. So things like dereferencing null or integer overflow don't have to be handled and declared in the interface. But for the most part, any exception that a method can raise has to be declared as part of its interface in Java. And then there are other mundane type rules about the particular design for exceptions in Java. So for example, throw has to be applied to an object of type exception. It can't be applied to an object of an arbitrary type. But overall, exceptions are rather nicely done in Java, and this particular idea of declaring the types of the exceptions that a method can raise was a new idea in Java.